Okay, so here's a standard statics problem. So let's read it together. So a physical therapist is testing the strength of a patient's bicep muscle. She has the patient hold a ball of mass M, okay, so that's over here, and radius R ball equals 10 centimeters in his hand. She increases the mass of the ball until the patient can just barely hold his arm at an angle of 105 degrees, which occurs at M equals 35 kilograms. So when this ball has a mass of 35 kilograms, the center of mass of the patient's arm is located 15 centimeters from the elbow. Okay, here's the elbow, and the center of mass is right here, and that distance is 15 centimeters. And the arm has a mass of, M arm is 2 kilograms. The patient's bicep muscle, actually let's write down the mass. Mass of the arm is 2 kilograms. The patient's bicep muscle connects to the arm 5 centimeters from the elbow joint. Okay, so here's the joint, and then they're saying that this bicep muscle is connecting 5 centimeters away. Okay, so they're asking us, what is the magnitude of the maximum force the biceps can withstand? All right, so this problem looks complicated because there's an arm, there's all kinds of stuff going on in this picture. I think it's usually a good idea to redraw the free body diagram and draw everything really clearly. And you want to take your time with this step because setting up the problem is the most important part. We're not going to have problems where you have to do tons and tons of math. You just have to make sure you know how to set the problem up. So let's just draw the arm as a stick. So here's the elbow joint, and then the arm extends out to the right like this. And let's make it bigger. Okay, so this is the joint. And then we have the bicep is connected 5 centimeters from the joint, and it goes up at an angle like this. So this is the force of the bicep, and that's at an angle of 105 degrees. And this distance is 5 centimeters. Okay, so what other forces are acting on the arm? Well, there are actually forces acting at the joint because there's a bone that's holding it in place. So there's actually a force acting at the joint at some angle. We don't know what it is. I usually, when I'm encountering with a force I don't know, I usually just split it up into a y component and an x component, just so I don't have to deal with sines and cosines in my initial equations. So there's a force, those are the forces from the elbow joint. And now we have the weight of the arm. So the arm is acting 15 centimeters from the joint. So we have force from gravity on the arm. And then all the way at the end of the arm, 35 centimeters away, we have the force from the ball, which is just going to be the gravitational force mg. So this is Fg ball. Okay, so now the picture looks somewhat similar, but most of this part is just making sure you understand, it's taking each little piece of the problem and making sure you account for each little piece. So you can think of it as bookkeeping. Okay, so now we know that we want everything to be not moving. We're looking at the point where the patient can just barely hold his arm at an angle of 105 degrees. So that's a giveaway that this is a statics problem. So usually when I'm doing a statics problem, I start with summing the torques to 0, because we know that if we have something in static equilibrium, we need the sum of the forces in the x direction to be 0, we need the sum of forces in the y direction to be 0, and the sum of the forces, the sum of the torques to be 0 as well. So I usually start with the torque equation, because sometimes in these problems that's all you need. So let's start with that. So the first thing you do when you're writing down the torque is you need to pick a pivot. And why do you have to do that? Well, the torque due to a force F is equal to R F sine theta. And what do these things mean? Well, R is the distance from the pivot to the point where the force is applied. And if we don't have a pivot, we can't figure out what R is. And theta is the angle between R and F. Okay, so let's try this. So I'm going to pick my pivot to be here, because I don't know Fy and I don't know Fx. And if I pick my pivot to be there, then the torque from both of these forces will be 0. So I'm going to pick that as my pivot. So summing the torques gives us, so Fy and Fx are both at a distance r from the pivot, so they have no torque contribution. The bicep, well, actually let's start with Fg ball and Fg arm, because they're easier. So the torque from Fg ball is going to be the distance from the pivot. Let's get another color here. The distance from the pivot all the way out to the ball, that's r. And in this case, let's call that's the 35 centimeters. Let's say that's r ball. Oh, I don't want to confuse it with the radius though. Oh, but that was capital R. It's fine. Our ball is 35 centimeters. So we have R ball times Fg ball. And then we need to do the sine of theta, or we can think of it as we want the component of the force that's perpendicular to the lever arm. They're at 90 degrees, so it's totally perpendicular. So sine theta is 1. Then is this term going to be positive or negative? Well, it's going to rotate, this force is going to tend to rotate the lever arm in this direction, and that's a negative torque because it's counterclockwise, so this needs a minus sign. Okay, so the gravitational force acting on the arm is also going to rotate in that direction, so we need another negative sign. Now we're going to subtract the radius to that force, so that's going to be 15 centimeters. That's the radius for the arm. So we'll do R arm times Fg arm. And now we need to deal with the bicep force. So we need to subtract the distance to the bicep, which is 5 centimeters, times the force on the bicep. And then we need to find the component of the bicep force that's perpendicular to the lever arm. So we're looking for this component. And I never like to deal with angles that are bigger than 90 degrees. So I know that because this angle is 105 degrees, this angle will be 75 degrees because the two have to sum to 180. And then I just have to deal with this triangle over here. So the y component is going to be F bicep sine 75. So I just need to sine 75 degrees here. And that all has to be equal to 0. So now, what were we looking for? We were looking for the force from the bicep. So we're going to want to solve for that, but let's see if we know any of these other things. And I'm going to need another page. That'll do. Okay, so we have our ball. Now, the force of gravity from the ball is just going to be the mass of the ball times g. And then subtract the radius of the arm times the mass of the arm times g. And then, oh, something is wrong. So which way is the bicep going to rotate the lever? It's going to rotate it counterclockwise. So this term should have a plus. So we need to add R bicep, F bicep, sine 75 degrees. Okay, so now we want to solve for this. So I'll put this term over here. Well, sep is R bicep times F bicep sine 75 degrees. Oops. And then I'm going to move these to the other side, so they're going to become positive. So we'll have plus, and we can factor out a g. We're going to have plus m ball, r ball, plus m arm, r arm. And then we just divide both sides by r bicep sine 75, and we get an expression for F bicep, which is all of this again. And then we want to divide that by R bicep sine of 75 degrees. And then we know all of these things, so you can just calculate a number and you're done.